That was
All right.
It sounded like a balloon.
Little review of definitions here. The identity matrix is that matrix with ones down that diagonal. And it's always a square matrix. And for every single matrix, you can multiply by an identity matrix and get exactly what you started with. Today we're going to learn about something called a determinant. The determinant of the matrix of an identity matrix is always 1. Here's the formula for the determinant of any 2 by 2 matrix. Notation-wise, we change the square bracket. We can either write determinant in front of a matrix or just change our square brackets to sort of like absolute value brackets. Now, this formula is much easier to remember with the following visual. You multiply this diagonal and then multiply this diagonal, and the blue one minus the red one is the determinant. Okay. So A times D, that diagonal, subtract B times C, that diagonal, and you get your determinant. So sometimes what I do when I'm showing my work, I might just go 8. The other diagonal is -9. Put a negative in front of that red diagonal. You're going to get 8 minus -9 and get 17. This one's 36. This one's 36. Put it in brackets and subtract. That one has a determinant of 0. Determinants of 0 are bad. They cause some trouble. Okay? Why do they cause some trouble? Well, first of all, you can only find the determinants of square matrices. Any other matrix you can't find the determinant of. And if the determinant is 0, we've got a new definition. We call this a singular matrice. And a singular matrix will not have an inverse. And we're going to learn about inverses today too. So you have to have that matrix determinant formula memorized for 2 by 2 matrices and also for 3 by 3 matrices. How is that? Basically what happens, okay, there's 2 shortcuts to remembering this. This blue part arrow here, if you take A and ignore everything else in the row and column that was there, you multiply by the determinant of what is left. Which then has this arrow and this arrow. Okay? Then you subtract B. So there's my B. I get rid of everything in that row and that column. And look at what's left. D, F, G, K. You have the determinant of that. Then you add C, same idea. Here's C, cancel out everything in that row and column, and multiply by the determinant of what's left. Now, there is also going to be a shortcut formula with lines for the 3 by 3, which I like even better than this. So you can remember how to do this one. Or you can remember the following. Same idea as diagonal lines, but you have to rewrite the first two columns. So A, B, G, B, E, H, you rewrite them. 3 diagonals this way are all your positive ones. 3 diagonals this way, add them up, and that's what you subtract. And that will be your determinant of your 3 by 3. So for me personally, this is easier to remember than the other one. Well, I remember them both, unfortunately. So I don't know if they're easier or harder. Don't worry, we won't have to do a 4 by 4. Or a 5 by 5, or a 6 by 6. You can do those on your calculator if you like. There is a DET button in matrices on our calculator, which we'll look at. So if I was asked to find the determinant of this next question, what I would do is I would rewrite the first and second columns. So there's me rewriting 2, 1, 2, negative 1, 2, 1. And then I'll have 3 blue diagonals, which will give me positive numbers. 3 negative diagonals, which I'll put in brackets, add them up, and think I have to subtract this one. And my determinant is negative 2.
What was in there?
I think originally I had it over top of something else, and then I didn't like it, so I just moved it up. To
Oh, okay.
But if you missed that, I can.
It's funny because there's nothing there. You would expect that there would be something there. It's usually those little boxes where you can seal something.
Drew's a big old jerk.
That's true.
Yo!
I second that. Can I have a turn?
No.
So try the next one on your own. I'll put up the answer in a second. Again, what possibly could go terribly wrong for you? Your mental math skills. Simple multiplication and adding could go wrong here. So what I'd recommend is take your time a little bit. Don't multiply too fast, don't add too fast. Because if you make a little mistake. Okay, you ready for the answer for the next one? How'd you do? Just waiting for Miguel to watch. Ready?
Yeah.
Oh, yes.
It's not there.
Ew.
What's not there? The joke is there, so it's fun. It's all you can tell about. I'm just rewriting.
Okay, we're gonna put this matrix into our calculator right now. So I'm gonna go to second matrix. I'm gonna edit. I'm just gonna overwrite A. So I'm gonna make A a 3 by 3. And we're gonna do this last one. 3, 0, 3. Negative 2, 1, 5, 4, -2, 0. And I often, also when I'm typing in my calculator, very easy to make a typo, so I just double check it quickly. And then, if you go to matrices, you can do all sorts of math with matrices. Determinant is the first one, so if we want to find the determinant of matrix A, we get 30, which is what we got before as well. It figures it out. If you have trouble switching your rows and columns for the transpose, there's a little T button. It'll do it for you. So under matrices, under math, we're going to use this determinant one. I think you can probably figure out the dimensions. Rows and matrices are off. Rows and columns, pretty good there. We also will use ref and ref. Those ones are pretty good. These kind of things, row swapping, we'll do on our own later on. But we will use ref and ref quite a bit. Okay. So. So the determinant one, that finds your determinant, which we just did. The transpose, it'll calculate the transpose, but you could probably do that on your own. And then I also have the ref there, which stands for row reduced echelon form. Okay, and we will do that a little bit later. Inverses of matrices.
If you spell it out and you sound it out, it sounds
This is the puzzle. If you want to find an inverse, so I'll just start with a 2 by 2, the smallest of matrices. 2, 1, 3, 5. 1, 2, 3, 5. I picked one that the mental math might be a little bit easy. But you're still going to get extremely stuck. What I want you to do is I want you to put numbers in there so that if you multiply 2, 1, 5, 3 by those numbers, you get the identity matrix. If you can discover what those numbers are, you have discovered the inverse for 2, 1, 5, 3. You could cheat and read ahead, but
Mansplaining it. I don't.
can anybody get one of the numbers? Which one did you get? You got a 0? What did you do to get which 0? This 0? So that if we're getting this 0, that's in row 1, column 2, right? So I need row 1, what did you put in column 2? Both zeros? That would work, right?
1/2.
1/2. Well, 1/2 and 0 would add up to 1. You need this one to add up to 0. You see how the blue, you're gonna wind these back, crash them into these, and you need to get 0. There's lots of different answers, right? That could work. I could use 1 and -2. Because then it would crash in 2 and -2, it would go away. So we have a problem here when we're just guessing and checking, because right now I have an infinite amount of answers that would work. So guessing and checking is going to be a problem. If we look at the next slide, it says if you want to find the inverse, it will always be 1 over the determinant. So AD minus BC, that's the diagonal here, AD minus BC, that's your determinant. And then we're going to switch this diagonal and make the other diagonal negative. Now I purposely chose one here. What's the determinant of this one? 1. I did that on purpose so that it would be a nice number. Now let's just see if this works. If I switch this diagonal, 3 and 2, and I make this diagonal negative, does the blue one, when it crashes in, get 0? It does. Let's look at this 1. This one is in 1, 1. So I would take row 1 and multiply by column 1. You see that I would get 6 minus 5 and get 1. And in fact, the other ones will work as well. Now, one of the things we had in our notes just before was about singular matrices. This is the reason why a singular matrix doesn't have an inverse. If the formula for an inverse has 1 over the determinant, and the determinant is 0, that's going to be a problem for this formula. Oh, I just want to show you math. I'm like, we're building up definitions, and I'm like, can't wait to show you what this does, but right now, here's our inverse. Find the inverse of these ones. We'll do one together. Right? Here's my is that the numbers I just picked?
Yes.
Yeah. Oh my goodness.
That scares me. That really scares me. Because it's the exact same numbers, and I was just being random. I was going to pick 4, but I thought Miguel thought I was going to pick 4, so I picked 5 to spice things up, and then it happens exactly the same. Oh, so let's not do this one. Obviously, we already did this one. And of course, this is what you discover when you multiply the inverse by itself. The determinant by its inverse will always be the identity matrix. But let's do this one. What is the determinant of this one? 3 minus 0 will be 3. So now this one would have a 1/3 out in front. Then switch the main diagonal and make the other diagonal negative. You can leave the 1/3 out in front, or if you'd like, you can put the 1/3 inside. Now I want to show you something on your calculator. Here, I'll move this over to the side so that you can still see that. I'm going to, wow, this is tough. Type in this one. I'm going to put it into matrix A, edit. It is now a 2 by 2. And I'm going to -3. 2, 0, -1. And I'm going to go over to math. Okay, now you've probably copied it down. This is super annoying to type halfway. I'm going to find the determinant. No, I'm going to find, clear it out. I'm going to find the inverse. So second matrix A, I want to find the inverse. Well, let's just use that -1 button. And sure enough, it figures it out. But what's annoying? The fraction. So you can still use the math fraction button and change your matrix back to fractions. And then you might see that you could factor a 1/3 out. So we can find inverses on our calculator with the inverse button. And any matrix matrix multiplied by its inverse is 1. In fact, it works if you put the inverse in front, it also equals 1. This is going to be important because it's the only thing that doesn't matter where you put it. All other matrices, A times B is not the same as B times A, which is going to come up as a special thing when we solve matrix equations. Right? And this is the note that we talked about before. If you have a singular matrix, if the determinant is 0, then there is no inverse. Okay, so I'd like you to enter the one at the bottom into your calculator and do that inverse button for yourself. I will do the reveal in a second.
Look at the trend.
Did it work on your calculator?
Or not, determinants.
And then you have to use the fraction button to get all the nice numbers. Otherwise, it's really full.
Imagine not using a fraction.
That's the real, that's.
I like the other bit.
Well, then you're just a trend hopper.
I'm not a trend hopper for Legend 345.
This is really hard. I keep wanting to show you more stuff with matrices. I have to hold back. But now we get to the first exciting thing where matrices can be used. You already know how to solve this equation. In fact, the way that you know how to solve it will be quicker than matrices at this moment. I would use elimination here. I would probably just take the top equation, subtract the bottom equation. The x's would go away very quickly. But we're going to do it with matrices. Okay? So if we are, it does say solve algebraically, so I would take this, I would subtract, my x's would go away. Negative 2y minus a negative y would be negative 1y. Negative 2 minus a negative 11 will be plus 9. So y is equal to 9. Negative 9, thank you. Y is equal to negative 9. And then once you have that, you could find x. 4x plus 18 equals negative 2. 4x equals negative 20. And x is equal to negative 5. That's using our elimination technique. So now we know what the answer is from our previous solvings. And you could double check, right? If this was your AP Calculus exam and you had this part, I'd probably plug both those back into both equations. They both should work. If they don't, then you made a mistake somewhere. Now in matrices, what we do is we take this equation and we rewrite it with a coefficient matrix A, a variable matrix X, and an answer matrix or constants matrix B. What happens when I do, check it out, matrix multiplication? You bend that one back, crash it in, and I would get 4x minus 2y, and what is it supposed to equal? Minus 2. That's our first equation. You see how that works? And the second one, you wind that back, crash it in, you get your second equation. So our coefficients matrix multiplied by our variable matrix equals the answer matrix is exactly the same equations that we had to start with. Now, if we call this one A, this one X, and this one B, how do you get rid of an A? There is no dividing in matrices. Matrix multiplication, there's matrix adding, there's matrix subtracting, and if you multiply by the inverse, you get the identity, and we have a property that the identity times anything keeps it the same. So if I want to get rid of this A, I have to multiply by A inverse. And this is the first thing that's different than regular math. Because in regular math, if you multiply both sides by something, you'd probably do this, times A inverse times A inverse, and this is completely wrong in matrices. Because A times B is not equal to B times A in matrices. So this would be bad. That's bad. If you multiply by the A inverse in front on this side, you have to multiply by A inverse in front on that side. That's going to be important. Okay, so now we're going to look at that same equation, and we're going to get -9 and -5. That's our hope. But we're going to use matrices, yes.
If it was x times a, I said a times x.
If it was
You then
x,
put equals b a inverse.
yes. So depending on where the A is. Of course, you can't write the variable, this is 2 rows, 1 column. This one is 2 rows, 2 columns. I couldn't put the A in front because that wouldn't make sense. Because then would not be compatible and you couldn't multiply those matrices together. Okay. So now let's go to this one that we just did. Our matrix A, there's our coefficients. There's our variables. There's our answer. These are compatible because it's a 2 by 2 times a 2 by 1. Now for showing your work, it's nice if you label them as A, X, and B because then you can multiply A inverse in front on both sides and get X equal to A inverse B. Because A inverse and A would go away to become the identity matrix. So we need to find our inverse. Our determinant here, -4 minus a -8, 1/4. I like to keep the fraction out in front. I don't like the fraction inside, just because mental math-wise, it's more annoying. So now this is what I have. I have the inverse in front times our answer matrix. This is a 2 by 2, this is a 2 by 1, they're compatible. I know that if I multiply these together, I'm going to get a 2 by 1. I still have that 1/4 out in front. And if I took, for example, if I wanted to find the 36, right? That 36 is in row 2, column 1, so I would take row 2, column 1, bend it back, crash it in, I would get an 8 and a -44. Add those two up, I will get -36. And we take 1/4 of that, we get our -5 and our -9, just like before. Okay. Now, I'm looking at the mental math here and I'm like, oh, elimination and substitution, I think I still like better in this situation. That's perfectly fine. I would probably agree with you. Okay. But as we get to 3 by 3, or if you had the use of your calculator, the matrices might be better. Okay. One of the things that sometimes comes up with different mathematical models, so we train computers to do stuff. Okay. And computers can do a lot of stuff, but even right now, what's the world doing? They're building all of these data centers because they have all of these people wanting to do all of these things all the time. And that takes time and it takes energy and it takes stuff. So we need to develop a system on the computer that does it the fastest possible, the most efficient possible, even though it's super fast. It can do some things inefficiently and still get them done really quickly. But if we can make them more efficient, then it can save energy. In fact, they used to determine speeds of calculators based on, speeds of computers based on, okay, computer, find me 1,000,000 digits of pi. How fast can you do it? Using this equation. And it takes some time to figure out 1,000,000 digits of pi mathematically. And so then they could say, oh, this computer is faster than this computer based on how quickly it could calculate something. All right, so we will leave the next two for, well, I'd like you to try this one. This is the next one. Try it on your own. Double check your answer. I'll put the answer up tomorrow. That's what we can do in the last 4 minutes.
I'll be the number one.